of the sum over I, sum over j, partial omega I, partial xj of dxj, wedge dxi1, wedge dot wedge dxik, right? Acting on the tuple, k plus 1 tuple. But of course, what's that? Oh, wait a minute. I'm back where I started. Why did I do that? Ah! That was dumb. Look at that. I come full circle. Good job, dummy. What should I have done? Probably think about and try and prove, maybe? I'm trying to get to the differential of exterior derivative of f pull back omega. All right. Oh man, what if I, just a second. I'm not sure where the hour mark hit, but it's not wrong, right? Just not. And I think even all right. So the next, so I shouldn't make, the step I made was not helpful. The red step, right? What I should have done, I guess, is this is what? This is the differential of sorry, what is the pullback of f pullback dxj is the differential of xj composed with f, is that right? I think this is true. Have I already proved that? I can't remember. I mean, fine, let's, if we're in doubt, let's work it out. It's funny. So, all right, the pullback acting on dxj. Now that's a particular one form, so we should let that act on a vector, right? And by definition, that is dxj, right? Acting on df of x. And so the claim is that that's equal to the differential of xj composed with f acting on x, right? Now that's definitely true for Fauché derivatives. That's the chain rule for Fauché derivatives. Is that true for our differential? Do we still have a chain rule for differentials? Okay. Ooh. Yeah, this is where, so in fact we do have a chain rule for differentials, and that's what we need to do this, all right? Or I just need to look at the definition with a clearer mind, one or the other, or both. But this is nevertheless true. Like there is, so that probably would be a good homework problem, is prove the chain rule for differentials. Like if I have the composition of two manifold maps, you know, if I've got like, let me state the rule I'm talking about here. If I've got M, and I've got N, and I've got a third manifold P. Oh, that's a bad choice. M, N, I don't know, I need another name for a manifold. Call it R. There. All right, and suppose you've got, you know, F goes from here to here, and G goes from there to there. Well, then you can talk about G composed with F, right? See, because G composed with F is a mapping from M, right? We start with P here, we go to F of P, we go to G of F of P, right? And so I can talk about the differential at the point P of G composed with F. And we can prove, in fact, that that's equal to the differential at P of G composed with the differential at F of P? No, G of P, right? Do I even have my composition right? I'm sorry, I doubt things. Okay, fine. This is the one that's wrong. F of P. Okay, duh. And then dP of F. Like that is something you can prove. That's a pretty good exercise. That becomes much easier as an exercise if you have the definition of the push forward in terms of the equivalence class of curves viewpoint. But anything, one thing for one day. Let's finish this here. So this is, in fact, the differential of x sub j composed with f wedged the differential of xi1 composed with f, wedgie, 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 the differential of I sub k composed with f, right? But what is that? What are we? And this, I guess you can take all of this jazz right here, right? All of this, and really repackage it as the sum over I, right, of the differential of the pullback of omega I wedged with the differential, you know, of xj composed with f. All right, well, I'm sorry, xi. Maybe I should have just left it. No, no. So that is, good grief. Stink. My mind is not working. Fine. xi composed with xi1 composed with f, wedge to that wedge, differential of xik composed with f, all of that acting on the k tuple, k plus 1 tuple, right? And what you're looking at there, maybe this is one of those calculations where I should just accept my fate and do a meet in the middle thing to be more convincing, you know? Maybe that'd be better. But this is the exterior derivative of the pullback of omega, acting on that, which is what we're trying to prove. We're trying to prove that the pullback of the exterior derivative is the exterior derivative of the pullback. But if you look at what you have here, you're differentiating the pullback of omega because we've got like f composed, you know, f composed with f here, and also basically we're substituting in the formulas for f in all of the, you know, coordinate directions there. So that would be, quote unquote, that would be the pullback of omega. We are differentiating the pullback of omega. Sorry if it's not completely convincing. I do think that the notes are pretty much 90% right. Probably more than, they're probably exactly right. This is something I got from my advisor, and it's pretty careful. Although I had a hand in it, so it could be wrong. So anyway, that's pretty much the proof of the, you know, properties of the pullback. Now, my example 10.73, I actually worked through the pullback for polar coordinate change, and I show in there that essentially the pullback amounts to substitution again, just like in my example 1. So anyway, we may do more of these. So the section 10.71 on intuitive computation of pullbacks, that's interesting. We should maybe spend a day playing around with that if there's time. I need to take a look at our schedule, make sure we got time, ask myself questions like which is more important, to spend time on that section or to sketch a proof of the generalized Stokes theorem, like which is a better use of time. I don't know. We'll think about it. Anyway, that's all for today.